Greetings, ladies and gentlemen, and welcome to the Astrophysics Group presentation. We are Team Quastars, and we are very excited to present to you all the research that we carried out over the past 4 weeks. Before we begin, however, a short explanation on our team name. The word Quastars is a wordplay between the celestial bodies of quasar and star. Quasars are one of the most interesting bodies in the known universe, known to have tremendous luminosity and energy. And that is something that we wanted to reflect on our team. We wanted all of us to be completely filled with energy whenever we were working or carrying out our research. Now, before we begin and presenting our research, we would like to give you a small introduction to all the team members. First, we have Pavina. She was our team leader. Following her is Neve. Neve was our assistant team leader. Following him are Shibam, Medansh, Subi, Azra, Akshara, Aditya, and myself, Drone. We also have Yunus, who wasn't able to join our meeting at this time. Now, before we again go on to the final the parts of our research, we would like to give you a table of contents which shows everything that we will be talking about over the course of our presentation today. The first, of course, is literature. This covers everything that we needed to know before we could begin our project. It set our foundation on the basis of which we could understand the problem statement and execute it. Second, we have data analysis and research. Here, we will give you a detailed walkthrough of the steps that we took to get to our results and what we actually got as our results. The third part are the conclusions. Here, we not only talk about what all we could infer from our results, but also how we could probably improve on our results and how we had our expectations about the research before we began the project and after we completed it. Fourth, we have the future. Here we examine how the possible ways that we could improve the methodology of our research, as well as discuss a future project that we could carry out as a team after this research program ends. After that, we have the experience at JSS, where one of our team members will be sharing everything that he got to learn and got to research in JSS and how he overall felt about the whole experience. And finally, we have the vote of thanks, which is our small way of showing gratitude towards all the members of the SSERD institution, without whom our research program would have been futile. So without further ado, I hand it over to Medansh, who will be starting us off with literature.
All right, thank you so much, Drone. I'm Medhansh, and I'm going to be taking you to the first 3 steps of our research, which are the stellar clusters, mainly the open clusters we studied. Number 2, the stellar evolution process, and number 3, the HR diagram, also known as the Hertzsprung-Russell diagram. Let's come to stellar clusters. What are stellar clusters? Stellar clusters, like the name suggests, are a group of stars. Now, for our research, we studied about open clusters. Open clusters are loosely bound groups of stars, which from few tens to few hundred stars. They are much smaller in size and much more sparsely populated than globular clusters. And open clusters are observed within many ranges of ages, from young stars to very old stars also. They are found in spiral and irregular galaxies. Now coming to stellar evolution. Stellar evolution is the process a star takes from going to a protostar to a main sequence star and finally to a giant star and finally leading to its death. Coming to the first step in the stellar evolution process, known as the protostar. In the protostar is created in large amounts of gas and dust, and the gravitational force of this infalling gas becomes very strong and eventually overwhelms the pressure which is holding all of this material together and forms very dense cores. The material then undergoes a very rapid collapse and the density of the core increases very much. During this time, a dense core is contracting to form a true star. But before the fusion of protons can begin to form helium, the star is called a protostar. After the protostar remains fairly cool with a very large radius and very low density. Because of this, the amount of gas outside the protostar's core can easily fall into the protostar. And because of this, the star shrinks, its surface area gets smaller and the luminosity decreases. The rapid contraction only stops when a process of nuclear fusion is achieved at about 12 million Kelvin. And at this point, the star starts fusing hydrogen into helium and enters a point called the zero-age main sequence, or ZAMS. This is the point where the star becomes a true star and spends its time in the main sequence. Now, what is the main sequence? Since during the nuclear fusion process, only 0.7% of the hydrogen used is converted into energy, the star's mass is not changed appreciably, but the composition changes and it spends a long time on the main sequence. But however, after some time, due to the changes in luminosity, temperature, size, and interior structure of the star comes out of the main sequence and turns into giant structures called red giants and supergiants. Later, after these structures exhaust all their fuel, they either burst in a humongous explosion called a supernova or turn into a planetary nebula followed by a white dwarf, depending on the mass of the star. Finally, we come to the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is the diagram made by two astronomers independently of each other, the Danish astronomer Ernst Hertzsprung and the American astronomer Henry Norris Russell. They made this graph in 1911, and it is an extremely important graph in stellar evolution. They plot the magnitude of the star against the stellar types or the temperature of the star. It evolved from the stars are ranked from bottom to top in decreasing order of magnitude and from left to right in decreasing temperature. And finally, there are three main parts of the Hertzsprung-Russell diagram, as you can see on the screen. The first, from the top left to the bottom right, is the main sequence. On the top right, we have the supergiants. In the middle, we have the giants, and on the bottom left, we have the white dwarfs. Supergiants are extremely luminous but cool objects, but while white dwarfs are extremely dim, small, but very, very hot objects. Now I hand it over to my other teammates to present the next slides.
So take a look at the diagram here, and I'm sure you can see some resemblance to the HR diagram we saw earlier. So this here is a color magnitude diagram. A color magnitude diagram is a variant of the HR diagram which shows the relation between the absolute magnitudes of the stars and their colors, which are closely related to their temperature and spectral types. While the HR diagram is a summary of the temperature and the magnitudes of individual stars, a color magnitude diagram is dedicated to the study of star clusters. The latter also plots spectral types instead of colors. The graph is plotted via the UBV photometric system, which is a system of classifying stars by their spectral type based on photometric measurements of ultraviolet denoted by U, blue denoted by V, and visual denoted by V. The V here is the measurement of the brightness from the Earth. So these magnitudes are measured through filters sensitive to light at wavelengths of 360, 420, and 540 nanometers respectively. So the color is represented in a numerical unit by the name color index. Color index is essentially the difference between two measurements of the magnitude of a star made at different wavelengths, where the value found at the longer wavelength being subtracted from that found at the shorter. This is simply denoted by B minus V as seen in the x-axis, as it is usually the difference between B and V bands. Now we move on to isochrones. An isochrone is a curve on the Hertzsprung-Russell diagram representing a population of stars of the same age but with different masses. Isochrones are designed to model our understanding of stellar evolution, and they can be used to date open clusters and globular clusters because the members all roughly have the same age. Their shape is likewise determined by the input parameters, so that an isochrone of a given appearance can be directly linked to its initial conditions. This allows us to state that a cluster and an isochrone which have the same shape must thereby have the same properties. Now my teammate Shibum will take over from here.
Coming on to the distance modulus. The distance modulus equation relates the apparent magnitude of a stellar cluster, which is denoted by small m, the absolute magnitude, which is denoted by capital M, and the distance of the cluster denoted by capital D. The equation is small m minus capital M is equal to 5 times log D to the BN minus 5 plus 80. And we get the final distance D in parsecs, and 1 parsec is equal to 3.26 light years. And we have modified the equation a bit, and the small m minus capital M is replaced by VC, which is the value of the V correction that we get by plotting the color magnitude diagrams for each of the open clusters and then comparing it with the color magnitude diagram of the zero-age main sequence stars of the ZAMS. And although we might think of interstellar space as a vacuum, it is in fact filled with a lot of gas and dust particles. And just like a smoke-filled room, the gas and dust particles along the line of sight to the star dim the starlight, by either absorbing or scattering the light. And we call this effect interstellar extinction. And if we do not account for this extinction, we might overestimate the distance to the stellar cluster. So to account for this, we have added the reddening factor that is denoted by AB. Next, coming on to our research statement. The problem statement that we have chosen is to determine the distance of open clusters by using the distance modulus relation. Now Neil will continue with our methodology.
Okay, so much of our data was derived from WebDA, which is a site devoted to open star clusters, and it is mainly intended for professional and amateur astronomers. So the data for color, the UBV CCD observations, were what we got from WebDA, and also data relating to the reddening factor, which we use to get AV in the distance modulus relation. To finally plot the CMD or the color magnitude diagram, we use TopCat, and to process the data for the equation that we use, the distance modulus relation, we made a Python code and processed the data to get our results. This is the color magnitude diagram for NGC 6633, and next to in blue and next to it in red is the ZAMS color magnitude diagram, which is the zero age main sequence. So to get the V correction values, we just had to align the color magnitude diagram for the open cluster with the ZAMS file and get the V correction value that we then input into our equation. So this is the Python code that we use to get our distance, and these are our results. As you can see, we have 10 open clusters along with their V correction values and reddening their reddening, which we use to get the AV value, and finally the distances that we got from our equation. Based on this, we can conclude that our analysis yielded an average error of 32% based on literature that we looked at from other estimates, and this excluded 3 clusters, NGC 6791, NGC 6603 and NGC 6031, which increased the error significantly to more than 100%. And this may be attributed to the quality of the data and the few computational errors associated with it. Another interesting observation was that 9 out of 10 clusters were for which we derived the distance. Our estimate for the distance was lower than the estimates. And now we'll talk about our future work.
So upon receiving these huge error margins, we are interested in finding out the reason behind it and how these margins can be corrected by either collecting more data or by looking into another methodology. So secondly, with the distance data, we would like to work on whether the clusters are intragalactic or extragalactic, which essentially means that finding out whether the clusters are within the Milky Way or not. So thirdly, we are interested in working on finding the age of open clusters. While we learned the methodology in this project, we could not go through with it due to time constraints. And lastly, repeating the same for globular clusters, which was something we could not do due to the lack of data.
Now that we have presented our research work, it is time for acknowledgements. First of all, we would like to extend a heartfelt gratitude towards Pratik sir and Anirudh sir, who were our mentors. They were like our guiding lights and were ready to solve any of our problems, whether that was related to doubts or concept, any obstacle that we had, they were there for us. In addition to that, we would also like to thank Professor Blesson Matthew for taking out the time from his busy schedule to spend some time with us and teaching us what all he has learned over the years of his research. It was a very enriching and interactive session, and we actually got to see how a modern day astrophysicist works. Finally, a massive thank you to all the members of the SSERD institution too. In addition to, of course, the weekly fun time sessions, which filled us with the energy for the week ahead of work. We also love the rigorous training sessions, without which our website, our research, how we present our research, our presentation skills, so on and so forth, would not have been possible. Now I would like to hand it over to Subi, who will be talking about his experience at JSS.
My experience with JSS SSERD was such a memorable one. I'm proud to be a part of Team Astrophysicist. physics or team pastures. We had voted our team leader, Pavina, and assistant team leader, Neil, who paved the way for the success of our team. We not only had fun, but we also learned a lot more new things about very interesting topics. Our mentors, Amit sir and Kritik sir, helped us to research and learn new things. We had never heard about most of the topics before we learned them in this program, and all of us have excelled in it. We had such supportive mentors and teammates. We had also done coding in Python to help us complete our research. And finding the solutions for such a fun and informative route we had. These 4 weeks were really interesting, fun, and a true memory that we will never forget. This program had fueled up our knowledge and propelled our willpower to achieve our ambition. Yet certainly cannot forget the Saturday fun time with Aditya sir, where we had fun, played games, had challenges, and shared our talents. It was such a stress reliever and extremely fun. We had great support from all our mentors, and we are proud to have them as our mentors. I want to thank all of them and my teammates for making this experience such a memorable.
Thank you all for listening to our presentation. I'm Medhansh, your moderator, and I would like to extend my gratitude towards all the SSERD team, towards my great team members who supported me and made this process extremely useful. I would also like to make a special mention towards Subi, who actually sacrificed this role of presenting a very important slide because of the time constraints and took up another role for the team's good. So I really applaud his team dedication and I really thank him for that. Also, now I would be opening the floor for questions. Thank you so much.
So you said you did V corrections to your clusters, right? So why did you do that?
Thank you, sir, for the question. I would like to send that question towards Neve, since he was the main instrumental person who worked over in this topic. Neve, would you like to answer this question?
Yeah, so as far as the equation goes, the difference in the magnitude and absolute magnitude is equal to the V correction is what we got. And as you could see, we had basically shifted to align the two graphs, the zero age main sequence, which is where 90% of the known stars are at, and align that with the open clusters under the assumption that it will have a similar range of stars. So does that answer?
Okay. Yeah. Okay, good. Also, how many types of these star clusters are there?
Since I worked on that topic, can I take that question, sir?
Anyone can answer. There is no.
Alright, so as according to our research and what you only our mentors taught us, we had found out 2 types of clusters, sir, the globular clusters and the open clusters. So we researched upon the open clusters, sir, and like how I said, the open clusters are smaller clusters which are consisting only tens to hundreds of stars, sir, and they're much more sparsely populated. But sir, globular clusters are very big clusters, sir, and they consist of at least few thousands to few millions of stars, sir. They're very densely populated also, and they're extremely big compared to the open clusters.
Okay. So do you think globular clusters would be far or near to, like you found the distance for your open clusters, right?
Sir.
So when you do it, so in your future work, you say you want to do it for globular clusters as well. So do you think there will be, the distance to that will be more than your open cluster or less than your open cluster? I mean,
Yes, sir.
answer this intuitively.
Okay, yes,
what
sir.
does your intuition say?
So my intuition personally says that they will be farther away because sir, they're larger bodies, sir. So and our Milky Way is also quite large galaxy, sir. So if they are quite large bodies, sir, like I said, they're a very large bodies, sir. So they will have to be far away from the Milky Way, not as close as open clusters. So we are expecting them to be farther away than compared to open clusters.
Okay. So just small correction to that would be, you know that the open clusters lie along the disk of your galaxies, and globular clusters lie towards the center of galaxies.
Yes, sir.
So it doesn't like it depends whether you are looking whether inside our galaxy or outside our galaxy. So the distance can be less and greater. There is no perfect value for that.
Okay, sir.
All right.
Also, is there anything, because you're talking about galaxies and the star clusters, is there any role of black holes in this distance? Would that affect the distance of the star clusters that are there between them? I'm not sure if my question is even right, but I just have that.
Could you rephrase your question? I didn't really understand what you meant.
So we're talking about the galaxies, and we also spoke about being in the center and outside, and we all know most of the galaxies would also have the black holes. And would that black hole have any effect on these clusters, and particularly the distance between them that we are talking? Like, is there any effect of black hole on these clusters, star clusters?
Would anyone like to take this question?
I don't think any of us are experienced enough to, answer that question, much less understand it completely. So,
Can I just jump in to clarify that?
Yeah, please.
Yeah. So if there is a heavy object between you and another object, there is an effect called gravitational lensing that happens, and that causes some errors. So to make it familiar with the work that the team has done, they have done something called as V correction, right? So that was to account for the extinction factor, the reddening factor, right? So in the same way, if there is a compact massive object between you, there is something called as lensing, and you have to consider some effects of that, and correction and suitable corrections to that to get your distances. Because if that happens, your direction of the star coordinates, everything will change. It like the object is at a particular coordinate, but it appears to be somewhere else because the black hole is in the line of sight with you and the star. So there will be some corrections that you will have to include there.
Okay, thank you, sir.
Good morning to all. As a parent, I want to place something as
Yes,
what I
please.
observed. I'm Muthukumar, parent of Minachanda Subi. And first of all, I will thank the SSERD team, which has done a wonderful thing for the entire team, which is presenting such a wonderful presentations. So it's a highly motivating, and it is definitely is going to fuel up the entire ideology of the new generation and their dreams, to fuel their dreams, and they provide a lot of knowledge and substance to go things. So we are literally delighted to be part of this, and please do more and more such programs. And yes, you are really creating the future leaders in this arena, and it's
Thank you so much, sir, for those kind words.